That's all, like whenever I restart, I just restart everything.
Oh, me too, though. Me too. I'm gonna put Julia tabs on now to sound like 10.
Well, no, my personal account's automatically on, like, it'll restore everything when I open it. Not right anymore.
Oh, I need to download Octa.
Octa?
I need to download that.
It looks kind of ugly, the interface, in my opinion.
Can I see it? It's not like Duo. Duo's pretty. Oh yeah, that was kind of ugly.
No, I lost my.
All right, hello everybody. Thank you all for coming. I think that clock is behind. I think it should be 4:30. So we can get started. This shouldn't take too long to actually get through all these slides. This is super informal, so please ask any questions you have. Just interrupt me. I don't care. I'm going to use this so that they can hear me on the lecture recording. So I'm sorry if you hear me twice. But this is mainly targeted for people who have never seen a circuit before, right? This is just going to get you all of the knowledge you should need to be able to do exam problems or homework problems related with analog circuits and stuff, right? So you guys probably figured this stuff out in lab already, but it's important to talk about how voltage and current work, right? So voltage is just the measure of electric potential between 2 points. And current wants to flow from a high voltage to a low voltage point, right? But it cannot flow without a connection between the 2 points. So it has to be a closed loop, right? That's the important part. So here we have 5 volts going through an LED on a wire, but there's no ground per se. There's no loop connecting it, right? So there's no current going through here, and the LED is not on. In this situation, we have a ground, right? There's a voltage difference here, 5 volts versus 0 volts. So current will flow from the high potential to the low potential, causing the LED to turn on. Make sense? Yeah, this is the very baseline point, but it's important to know for when you're analyzing your circuits, you know where the current's going. So then we can talk about loads. So as I was talking about before, we can think of these batteries as a voltage potential, right? That's all batteries are. They supply power. So we have a positive terminal on this side, a negative terminal, and we have a wire connecting the two. So we have a full loop so current can flow, right? You guys probably use this in lab as well. Voltage equals current times resistance, right? That's how you calculate it. That's what you did to find the resistor you used for your current limiting resistor for that LED in lab 1. But we have 3 scenarios here, okay? So we have a battery with the voltage difference, right? And then we have it's going through a resistor, through an LED, back to the battery. So this is the exact same setup. You can think of the STM as the battery in that case, right? It has 3.3 and it also has a ground. So this is the loop, right? This is good. This is good. This is bad, right? We just have a wire connecting the positive to negative terminals. Does anyone want to take a guess at why this might be bad? It kind of says it on there, but why is infinite current bad? Sure.
Make the wire really hot and stuff.
Great, exactly. Yeah, as current moves through all of our components, it generates heat, right? Power is dissipated as heat. So if we look at our equation, we have a voltage difference here, so we can say it's 3.3 volts, right? Ideally, when we model circuits, we like to treat wires as having zero resistance. So if we have zero resistance, then the current has to be infinite, right? This is not a real circuit. But if we have infinite current, we're generating infinite heat. It's just, your wire's just going to melt, OK? Which is why we had you guys find that current limiting resistor for your LED, so we didn't put too much current through it and blow up the LED, right? Same idea there. OK, and then in this third scenario, let's say we cut our wire. Why isn't the LED on in this case? Right. No current, right? It's not connected, so it can't flow from high to low. I know not all of you have done lab 3, but for lab 3, when you make your MMIO and you do the read port with the tri-state buffer, and we talk about a high impedance mode, this is high impedance, right? There is no way for current to flow through here because it's disconnected, right? So that's when we say in the tri-state buffer, in the high impedance mode, you can think of that part of the circuit as disconnected. It's the same idea. It is physically disconnecting the wires, causing it not to influence the rest of the system. Do these three make sense? Is this intuitive? OK. Now we can talk about analyzing circuits and simplifying them. Circuit nodes are the main way you identify places you can simplify stuff. So in between components, there's always going to be a node, right? So between this positive terminal of the battery and this resistor right here, that's a node. Between these two resistors, this is a node. And then between this resistor and the top side of these two resistors, there's a node. And then finally, we have a ground node, right? All of these different colored sections are different nodes on our circuit, OK? And you can use that to know, obviously, what's connected, but also how you can simplify them, right? So here, we see that there is one node that is only connected to this side of a resistor and this side of a resistor, right? It's going straight and straight. So this is what we called in series, OK? When they're back to back and there's no branching off, these two resistors are in series with each other, OK? On the other side, we have a node here that's coming out of this resistor, splitting off and going through two different resistors, right? These two resistors are in parallel, OK? It splits off and goes into both of them. And how you simplify them is a little different. So in series, these two, it's additive, OK? So the equivalent resistance for these two is just R1 plus R2, OK? And then in parallel, it's a little different. This equation right here is great. So we have 1 over the total equivalent resistance is equal to 1 over our first resistance plus 1 over our second resistance, OK? So let's pretend R3 is 10 ohms and R4 is 10 ohms. Let's just make it super easy for ourselves, right? So we take 1 over 10 plus 1 over 10 is 2 over 10, which is 1/5, right? So then we have 1 over 5 is our total. So our equivalent resistance is 5 ohms, OK? This means you could get rid of these two resistors, just put 1 here, and make it 5 ohms, and the circuit would behave the same exact way, right? So I think we should find the equivalent resistance of this entire circuit, OK? So we have our battery going into R1, going into R2, and this splits off and goes into 2 resistors. Don't mind my drawing skills. It's not great. OK. So we already talked about the parallel case, right? We talked this. Our equivalent is 1 over R3 plus 1 over R4 is the equivalent for this section. And we already talked about the other one is R1 plus R2. So then we can simplify this to be the battery is through one resistor, that is R1 plus R2 in resistance, right? And then we also said we can simplify this one to be 1 over R3 plus 1 over R4. And so we have these two resistors, right? And now that we simplified those two subsections of the circuit a little bit, we can see that now these two equivalent resistances are in series, right? So we can go ahead and add them like we did the first case. So overall, this would break down to, or not break down, simplify down to one resistor that has a resistance of R1 plus R2 plus 1 over R3 plus 1 over R4. Okay, does that make sense to everyone how we, step by step, how we simplified that? Okay, great. So this is super useful if you need to determine how much current is going through your system, right? So now we have, let's just say the battery is 3 volts. So we have 0 volts here for ground. And then we have this. If we used this one up here, it would be a lot harder to find out how much current is going through our system if we have all these random resistors, right? But now that we're modeling it with just one battery or one voltage source and one resistor, it's super easy, right? We have our V equals IR. This equivalent resistance you can put here, and then you have your voltage, and then you can just solve for I, right? So this is a great way to simplify whatever you're modeling and find out the current. Does this make sense? Great. Okay, so this is, oh, I had values. I didn't even realize that. Okay, let's plug those in real fast. Let's do this problem. So we have R1 equals 5K, R2 equals 3K, R3 equals 3K, R4 equals 6K. Okay, so we already found the equation. We can just plug it in. We have 5K plus 3K plus 1 over 3K plus 1 over 6K. So this can simplify down to 3 over 6K, which is 1/2, right? So 1 over 1/2 is 2K plus 8K. So our equivalent resistance is 10,000 ohms, right? When we plug in those numbers, we already found the equation, so that's fine. And then we use the V equals IR that I was talking about before. So we have 3 volts. I think I said 5 in the other one, but it's fine. I times 10K, divide both sides by 10K. So you have 3 over 10K amps, which is really small. So your circuit would be just fine. Okay, cool. All right, everyone feel good about resistors? That all makes sense? Great. Okay, now we have capacitors. I think these are a little harder to think about. Simplifying them is fine, but what they actually do in the circuit is a little different. Capacitors hold charge, and they're not supposed to let current conduct through them, okay? They might leak a little bit, and that's just because physics stuff. But in theory, you should never have current flowing through a capacitor, okay? Because they can hold charge, they're mainly used to reduce noise and stuff, okay? So, any markers? Let's see if any of these markers work. So let's say we're building a system. This will be a graph over time. This will be our voltage, okay? Let's say you're building a system. It's supposed to run on 3 volts. Oh, that's an awful 3. It's supposed to run on 3 volts. Let's say that's right here, okay? V equals IR, right? Like that's what we said before. If you have a system and it's running and then all of a sudden maybe you get some input from something and you have to do a bunch of computation right away, your current draw is going to jump up a bunch, right? Because your CPU needs to do a whole bunch of stuff. Maybe the thing that took the input draws a lot of current, right? Because your current goes up a lot and your resistance isn't really changing because your circuit is set, your voltage is going to droop a little bit. So your voltage curve is going to be pretty steady, and then it might droop a bit at your incident, okay? This is where capacitors come in. If you put capacitors on your voltage source, so we had the battery like before with the plus and the minus. I guess maybe I should explain that first, but let's say we have a capacitor here, right? This holds charge. So while the voltage is steady, this is going to hold some amount of charge, depending on the capacitance of your capacitor, at 3 volts, or whatever your plus is, right? In this case, it's 3 volts. When you have a sudden inrush of current and your voltage wants to droop, what's actually going to happen is this charge is going to want to keep this node at 3 volts, right? So it will actually supply charge and supply extra current, which will fight this voltage droop, right? So as you supply more charge, maybe it only droops a little bit, and then your system's good, right? That's the general idea of what capacitors are used for, to eliminate sudden droops or peaks in your system. Does this make sense? Okay. If you ever do PCB stuff, like this is super important. Okay, so now that we have them on our circuit, how do we simplify them? It's actually the inverse of how resistors work. And we can imagine why. So as I said, capacitors hold charge, right? And they hold charge proportional to what their capacitance is, right? So if we have a capacitor, let's just say it has a capacitance of 10, okay? And it's here, and as I said, it charges up in steady state, right? We add another one that has a capacitance of 10, right? If we encounter something like that voltage droop, which one is going to be able to supply more current to the voltage? Just the one with 10 capacitance, or 2 of them with 10 capacitance each?
One with both.
Both, right? So now they're both holding the charge. You have double the charge to supply current, right? So when they're in parallel like this, they're additive, like how resistors were in series, right? And that's just because the total amount of charge they can save just adds up on the same node. And then same thing when they're in series, it's actually the same as when the resistors are in parallel. It's 1 over the capacitance plus 1 over the capacitance is 1 over the equivalent total capacitance, right? This was pretty counterintuitive to me at the start. Normally, you don't really put capacitors in series like this. But what capacitors actually are 2 metal plates that are super close to each other that are separated by a dielectric, okay? Basically, they're coupled with each other, and charge wants to move from one side to the other, right? That's why charge sits on the positive plate of the capacitor and can't move to the second one, because they're separated by a dielectric, right? If you have 2 in series, you have a voltage here, and then you have some intermediary voltage, and then less voltage. The capacitance on a capacitor is actually determined on how far apart the plates are from each other, right? The closer, the more coupled they are. By physically putting 2 in series, you're essentially making it so this plate is coupled with this plate. So the total capacitance will go down because they're further from each other, right? Okay. Does this all make sense, all the capacitor stuff? I think they're less intuitive than resistors. So if you're confused at all, please let me know. And then our final component we're going to talk about. For us in this class, these are kind of the only 3 you really need to know: resistors, capacitors, and diodes. And because diodes are super important, and also we use a lot of LEDs in embedded systems. And those are diodes. They're light-emitting diodes, right? But other than just creating light, they're used to control current flow. okay? Current can only flow in one direction through a diode, all right? This is the symbol for a diode. So normally you can think of this bar as like a wall, right? Current can move in the direction of the arrow, but it can't move against it, right? These are great. So we have this first one on the left has a positive voltage up here, a current limiting resistor, and then a diode facing the right direction, right? So we're going to get, based on this calculation, we're going to get 5 milliamps through this diode, through this whole circuit, right? We have the voltage drop as 0 here. It's not realistic, but this is just for teaching purposes. In this scenario, we have the diode flipped, okay? And as you can see, there's 0 milliamps going through this because this is blocking it. The current can only flow in one direction. So this is actually equivalent to being an open circuit or high impedance mode, right? So you can do some really cool things with diodes to do voltage rectification, right? So there's two types of power. There's AC and there's DC, right? Alternating current and then, what is DC? Direct current? I'm not sure. Basically, it just means it doesn't alternate. So your AC voltage is going to look like this, right? It's going to alternate from positive whatever to negative whatever, right? Pretty much all of your devices, anything that takes power from a wall, needs to rectify that to be only positive. Most things can't use negative voltage, right? And that's what, on all your chargers, the little power bricks, this is actually what it's doing inside. You can use these 4 diodes to make it look like it's always positive. It'll get rid of this negative portion. So we can look at why that is. So this is our voltage source. This is this signal, right? Alternating. Let's say it's positive here and negative here, just for this point, right? It's positive, so the current flows from here. It'll flow through this diode, cannot flow through this diode, right? Goes through the resistor, comes back up here, flows through this diode, and it can go through this one, but it's just going to meet all the way back around, so it's the same thing. And then it goes back to the negative part, right? So we've induced positive current through this resistor, right? This is our load, whatever, your laptop that's charging, phone, anything that's using the power, right? So what in this scenario when it's negative up here and positive down here, right? So if it's positive here, it wants to flow to the negative, so it'll come through here, can't go through this diode, has to go through here, goes through the resistor, positive current across the resistor, comes back here, again, could loop here, but it's just going to do a loop, so it goes through here, back up to there. And so no matter if you have positive or negative on that side, you're going to get a positive voltage. So that's the kind of things diodes are used for. I guess I can briefly talk about this. This is kind of what you solved for in lab, right? You put a certain voltage on it and then let it go up to however much current, right? And that's how you got your forward voltage to calculate that, your current limiting resistor. But how diodes basically work, they have a voltage at which they turn on, and then they can conduct, I mean, not literally infinite, but after you get to the forward voltage, if you go up much more in voltage, you're just going to blow it up because it can support so much current going through there, which is why you need the current limiting resistor. And that changes depending on what it is, right? The reason we had you guys all use those clear LEDs is because there are a bunch of different colors, right? And depending on what the color is, it's going to be a different voltage drop. So like blue has the biggest voltage drop. I think red has the least. But yeah, that's how diodes work. We're in an embedded systems class, so we're going to talk about Zener diodes for power regulation. Similar to this scenario over here where we have a voltage droop, where it went down and we were risking a brownout. Zener diodes are especially useful when we have something like a voltage peak. Like let's say you had a power surge on your voltage supply for some reason. Right here, this could overvolt your system and maybe fry your CPU. Or fry components, could permanently ruin the board, right? That would be pretty bad. So what we do is you would have your capacitor here, of course, but it charges up, so it's not really going to fight this a whole lot, right? It can only absorb so much charge. So we can pretend that's also there. But we'll have something called a Zener diode right here as well, okay? So as you can see, it's facing in this direction, so current can only flow through this way, right? So no current is flowing this way. So under normal circumstances, this has no effect on the circuit, right? Zener diodes are special because I'm not going to pretend to know the physics, but they can change the breakdown voltage of a diode. So the breakdown voltage is you get such a big reverse voltage on it, so voltage where it's basically a negative voltage across here, right? A super big positive voltage on the wrong side of the diode. It actually breaks down and conducts current. Okay, so it breaks the diode. Normally those are really big for like LEDs and stuff. You would have to put a huge voltage on them to be able to do that. These are specifically made to have known breakdown voltages, okay? So let's say your system is 5 volts in this case. And let's say if your system hit a 6-volt peak here, everything would break, right? You would put a Zener diode with a breakdown of maybe something like 5.5 volts, right? And so as soon as this gets up to this point or gets over 5.5 volts, this diode is going to break down and allow current to go through it, right? Effectively, letting all that extra current or voltage that's peaking to have a super short path back to ground, and it'll flatten it out, and you won't fry your board. This will be broken, but it's a lot better than your fried board, right? So this is super important in power regulation as well. Right. Does anyone have any? Yeah.
It's just the same concept with the fuse.
Yeah, pretty similar. Yeah, so like a fuse, if you put too much current through it, it'll break, and then you have an open circuit, right? High impedance. This is just, yeah, this is another way. If you had like a fuse through here, if you had too much current, yeah, it would be the same thing. Cool. Yeah.
When it breaks down, does that become a short?
Not entirely a short, but pretty close, yes. It will have some resistance, but I mean, the main goal is to dissipate as much extra current as you can, right? And then once it gets below 5.5 volts, it will stop conducting, so it'll just dissipate that extra power. You won't have to worry about it like shorting your entire system. Does that make sense? Okay, cool. Does anyone have any other questions about diodes? Sure.
Does it not get ruined at like the really low voltage or the really high reverse voltage?
Yes, it will break it. Sorry, it won't break it. It's called breakdown, as in it's breaking down the valence band that it actually puts electrons on, because you're putting so much force on it that it's shooting electrons over the band in the wrong direction. Once you remove that voltage, it'll go back to normal. Yes. Okay. All right, we're going to talk about voltage dividers. This is going to be super important for lab 5, I believe is ADCs. It's either lab 5 or lab 6, ADCs and DACs. This is basically a way to take any voltage and get it to the voltage you need, right? It might not be super power efficient. That's a whole nother problem. But basically, it's just using the resistors we talked about to make a divider. So it's just 2 resistors over voltage, and then you should be able to get any voltage between your high voltage and 0 volts, obviously. Yeah, these are all ways you can show them. I like the one all the way on the left, where you have your voltage source, you have your 1 resistor, 2 resistor, then ground, and then here is your V out, whatever, right? So you have R1, R2, and then your VDD, your source voltage, right? I already gave you the equation. This voltage is V out equals V in times R1 divided by R1 plus R2. Yeah, we can go through how we derived this. Okay, so these are in series, right? We agree with that? They're back to back. This is branching off, but this is just us looking at the voltage at this node. It doesn't necessarily mean that it's branching off and going to a different path, right? So our total resistance is R1 plus R2, right? And then we have VDD equals the current through these two resistors, right? So what if we just want to see this section, right? We know the current. The current going through there is VDD over R1 plus R2, right? This is the current going through each of these resistors. But we want to find out this internal node. So we can take the source voltage, right? And then we could subtract the voltage over just this resistor, right? And that's VDD, that is the current we found earlier times just R1, right? So we can plug that in here, and we have minus VDD over R1 plus R2 times R1. Yes, I'm going to rename this for the naming schemes we have here. So V out, VDD. Okay. Equals V out. Did I do something wrong? Oh, no, this is the voltage. Okay, sorry. No, yeah, this is right. Is this right? Are you guys following along? Did I do this wrong?
Can you just go over the last part? Like, how do you know the V out from these equations?
Okay. So let's do a real numerical example. Okay, we have 3.3 volts here, right? Say that's 1 kilo ohms, this is 2 kilo ohms, right? We're trying to find out what V out is here, right? As I said before, VDD is equal to the current going through, so we have 0 volts here. So we know the current going from here to here is going through these two resistors. So this voltage should equal the current going through both of these resistors, right? Because they're in series. So we can solve for the current here. So we have 3.3 volts. 3.3 volts divided by 1K plus 2K. Actually, I'm going to make this 3. So I have to do less math. By 3 kilo ohms, okay, equals our I. So that gives us 1 milliamp. Good? Okay. So now that we know how much current is going through the whole system, we can find out the voltage drop across this resistor only, right? Because before we solved the current for the total thing, but now we can solve it for just over this resistor with the V equals IR. So we know we're solving for V. We know there's 1 milliamp going through here, and we have a 1K resistor, okay? So that means the voltage drop is 1 volt across here. Does that make sense? So then we can take the total VDD that we have, 3 volts minus 1 volt equals 2 volts. So we know 1 volt dropped over this. So we know this node must be 2 volts. Does that make sense? I feel like that was a little convoluted. OK. This is the same thing we would get using this equation. Let's use that equation. This is a simplified one. It's super easy to remember. If you're doing voltage divider stuff, just use this. I'm just explaining where it came from. So V out equals 3 volts times, do I have R2 as which one? The bottom one, OK. Times this bottom resistor, right? 2K, because essentially we're looking for the voltage drop from here to here, right? Do we agree with that? That's the voltage at this node. 2K divided by 1K plus 2K equals, those cancel out, and we get 2 volts. So same answer. Does this make sense? OK. So let's say you had, maybe your battery was 5 volts, right? Your battery was 5 volts, and you wanted to get, let's say your CPU takes 3 volts. Right? So you have your battery, 5 volts, 0 volts for ground. And let's say you have your, we can just model it as a resistor. But let's say this is your STM, right? This needs, we'll just say 3 volts. It's really, they take 5 and then go down. But for this example, let's say it needs 3 volts, right? We could use a voltage divider to get down to these 3 volts, right? So we need to drop 2 volts and save 3 volts, right? So what if we did, I dropped it. What if we did, actually, no, I'll ask you guys. Let's keep it in the thousands, just so we don't have too much current. But given that we have 5 volts and we need to go to 3, what do you think good values for these might be, ratio-wise?
So we have 5 and we want 3.
Yeah. Let's say in this example, we have, I'll erase it. We have 5 volts up here. And we want 3 volts right there.
So I guess we could have the bottom one be like 3 is like 3:2, so it would become 3/5 and 2/5.
Right? So then if we translate that to thousands, we can put a 2K resistor here, 3K resistor here. It's 5K total. And we have 5 volts. So we know it'll drop 1 volt per 1,000, right? And we have 2,000, so it'll drop it down to 3. Does that make sense how she did that? OK. So yeah, you can use these just to find a ratio to drop that down. So if we had the 2K here, the 3K here, and we took this voltage, put it on, we'd have 3 volts here, and we wouldn't break our processor, right? In reality, you'd probably use a linear regulator or a buck for this to drop the voltage, but this is just for principle. So how I said this is going to relate to your lab, you're going to be using these things called potentiometers. Okay, this is what they look like. It's a 3-terminal system, and it has a knob that you turn. Okay? Sorry. And it has a knob that you turn. Okay? And how you use these things. How you use these things, you put a voltage on one terminal, right? So 5 volts, 3, whatever. Put a ground on the other side, and this middle terminal is the middle of the voltage divider, right? So these are variable voltage dividers. So how they work is one pin has the voltage, one has ground, and this is one long resistor, okay? So the resistors you're probably used to seeing in lab, like the ones with the 2 wires and then the ceramic thing in the middle, right? the total resistance over the entire thing is the labeled resistance, right? But if you were somehow able to break it open and measure exactly halfway, you would only get half the resistance, right? It is literally dependent on the full length. So what we can do here is have a middle terminal that can move across this entire resistor, right? So as you turn it, if you put it here, you would get half the voltage of your input, right? Because it's halfway across the resistor. Does this make sense? Same with if you put it a quarter, 3/4, right? It drops variable on how you turn it. Actually, I guess you guys might not even know what ADCs and DACs are before you do that lab. So an ADC is an analog to digital converter, okay? So it takes in an analog value and it gives you a digital value based on that, right? So you're going to use these potentiometers in lab. You're going to put 3.3 volts on the positive terminal, ground on the other side, and then you're going to hook up this middle pin to your ADC, right? And you're going to see as you turn it, the ADC is going to give you a different value as the voltage is changing, right? So you could use this as a user input, right? If it's in the top half, do something. If it's in the bottom half of voltage, do something else, right? Or you can use it as a volume knob, some stuff like that, right? That's how you can use variable voltage as an input to an embedded system. Does that make sense? I guess I'm kind of hand-waving this because you guys haven't learned about this yet, but yeah, okay. This is probably going to be the most common thing you'd see on an exam that like you might need to know is voltage divider stuff, or taking like 3 resistors in series and figuring out the voltage at a node, right? So this is definitely something I would recommend knowing.
But can I ask a quick question?
Definitely, yeah.
This isn't relevant to the question that you just discussed.
Sure.
But like on the in the voltage divider on the very left, if at like V out, if there was like a resistor, like are the 3 resistors like still in series, or like is that just like not anything anymore?
So technically, no. That would be like, here, I'll draw it out. That would be like before where we could find a equivalent resistance. Are you saying something like we have a resistor and then that goes to ground as well?
Yeah.
Yeah. So technically, these 2 are in parallel.
Right.
So you could simplify them and then simplify and then find the total voltage. But technically, the circuit itself, when you talk about a circuit as a whole, it either has to be fully in series, fully in parallel, or it's somewhere in the middle, right? And this one, we go through here, but it branches out to parallel, so this is technically neither. Does that answer your question, or did that make you more confused?
So like the one on the top is like in series, or like the 2 on the bottom as a pair is in series with the one on the top. Is that what you're saying?
Yeah, you could think of it like that. Yeah. Yes.
So if we're using that as a voltage divider, like we take the V out pin and then we connect it to a resistor, wouldn't it mess with the actual input voltage we end up getting from the voltage divider?
Yes, it would. That's why most of the time, when you do this, you guys also haven't learned about this. You would put a buffer here. This is also important, probably not on this exam, but we will definitely ask you something about this on the second exam. You'll learn about what output buffers are. Basically, they take in an input voltage, right? In this case, we had 3 volts here, and it isolates it from this side. So you can guarantee you put 3 volts here without letting this circuit affect here, right? So current, you can kind of think of it like a diode, but it has a bunch of transistors and stuff. But essentially, current can flow this way. Current cannot flow this way. From this resistor's perspective, it's like it's an open circuit, and it's just getting 3 volts from somewhere, right? So this doesn't affect our output voltage here. You're totally right. If you just hooked up this here, this equivalent resistance would be different, and then your ratio would be off for your voltage divider, right? So you'd use an output buffer there. I'm sure you'll come back to that when you actually learn about it. But yes, great question. Any others about this? OK. Breadboards. You guys had to use them in the first lab. I think we talked about them a little bit. You will definitely need to use them in future labs, and you will definitely use them on your project. So I'm just going to briefly go over them because not everyone knows how to use them. These inner columns right here, so everything inside of what are called the rails out here, are connected vertically. Okay? So if you see like these numbers at the top, row 5, all of these in row 5 are connected to each other, right? I see a lot of people like put a resistor from here to here in the same thing, and that's essentially shorting the two of them, which is probably not what you want, right? So if you want it to move from one spot to the other, you'll have to go horizontally across this. Does that make sense? The inner works? OK. And then these rails on the outside are all connected horizontally instead. So like if you follow the black stripe or the red stripe, all of the pins on either the top or the bottom should be connected with each other, right? So these are commonly used for like a ground rail, because everything you use is going to need a ground connection, or a voltage rail, because everything's going to need a voltage rail as well, right? One thing to know, though, sometimes when you have these long breadboards, I think you guys might have smaller ones, but we definitely have longer ones. Sometimes the rails are not connected across the middle. So you could connect your ground to your board here and then be using it for some components here. Try and grab off of it on this side, and it's not actually going to give you a ground connection. It's like a super common thing. I wired everything up correctly. I double-checked the circuit. Like, it's not wrong, I promise. And the issue is just that it's not actually connected. So if you use these, either stick to one side or just put jumpers between this one and this one to make sure they're definitely connected. Yeah, just something to be aware of. False add. You guys had to use this in homework 1, right? Yeah, so you guys have experienced it a little bit. This is super helpful for your project. If it's not necessary that you guys make analog circuits, some of you will probably have to for whatever project you guys pick. Model it before you make it. I promise it will make your life 10 times easier. You won't have to measure stuff on a breadboard with a multimeter. You can just model it in Falstad and look at all the values anytime you want. And also, if you're trying to make a circuit from scratch and you want one of the staff's help with it, having a model will be super helpful because we can look at it exactly and see what you're trying to do. Sometimes it's hard to look at a physical circuit and understand what it's trying to do right away. But a Falstad circuit, super easy to understand. And it's also super easy to modify stuff and just test stuff, right? So if you do that, please do that before you come to us for help. We'll obviously help you no matter what, but that will help a lot. Yeah, I have the link. That's just the link to your homework 1. How do we feel about Falstad? Like, if you guys were to make a circuit, do you feel like you could go on Falstad and make one? Yeah, OK. Then we don't have to go over that. I think that's pretty much it. Yeah, so this is stuff I base it off of. These are longer articles that you can go read if you feel like I glazed over something. But yeah, this is where it's all from. And these slides should be on the... when you guys go to the class website, they should be with the rest of the slides. I'm going to double check right now, though. And add slides. Oh, fine. I guess so. Great.
I think they are. I was able to download them.
You can see them? OK, OK. Yeah, so these are available there if you ever want to look at them. Again, yeah, I guess that's everything I have. Does anybody have any questions about what I covered? Anything adjacent that you just have questions about? I'm more than happy to answer anything. Yeah.
We're gonna have to know pull up and pull down resistors.
Yes, we should absolutely go over that. That's great. Thank you for bringing that up. I'm going to draw them here so it's easier to see. Yes, so output buffers for exam 2, you're definitely going to need to know. Voltage dividers, I would definitely know for both exams. And then pull up, pull down, yes, definitely. Thank you for bringing this up.
Can you also explain the output buffers again?
Yes. I will do that after, yes. Okay, so we have our pin, our CPU pin, right? And then we have our voltage source, and we have a resistor, and then we have our button, and then we have ground, right? So this is one configuration. That's a pull-up resistor. We'll get into why that is in a second. We have our switch here, our voltage, and then we have a resistor here, okay? Okay, so these are the two configurations. This is for your input pin, right? This is for when you want to read the input from a button, okay? So the way, actually, let's just analyze the circuits. Okay, so here, in this circuit, we don't really care about the resistance value for now. When this switch is not pressed, what is the voltage on the pin? High, great. Whatever our voltage is. We'll just call them 3 volts. So yeah, you'll get 3 volts here, and you'll get a 1 in your processor, right? And so when you press the button, this is pressed down, what value goes onto the pin? 0, right? So you get 0 volts here, and we'll read a 0 onto our pin. Great, so this is good for the first one. For this one, when the button is not pressed, what do we get? 0 volts, and then when it is pressed, 3 volts, right? So it's inverted. So in this scenario, so how you can look at something and know whether it's a pull up or pull down, that's kind of what trips people up a lot, and sometimes that's what we ask, right? What is this circuit? Is this a pull up or pull down resistor? Or we'll ask you to draw a circuit, like an input pin, and say use a pull up resistor, right? Something like that. I like to think about when the button is not pressed, when the circuit is just sitting there, no one is interacting with it, what is the value on your pin, right? In this first case, when no one's touching it, no one's using the switch at all, it defaults to 3 volts, right? So it is pulling the pin up to our voltage, right? It's pulling it up to a 1 by default. Same thing here. When no one's touching the switch, by default, it is pulling it down to ground, down to a 0, right? So that's how I would think about it. If no one is touching the circuit, what is the default voltage on the pin, okay? I think we went over this a little bit in lab, but like the reason we need these, right? Let's say we took the pull-up circuit and we just didn't have a pull-up resistor, right? When this button is pressed, we'll get 0 volts here, right? That's what we determined. When the button is pressed and then let go, what's the voltage on the pin? Great, we don't know. We don't know what the voltage is, right? It could be anything, it's floating. It's not connected to any nodes or any voltage sources, whether that's ground or 3 volts. So we need a resistor to pull that up. That's where the name comes from, right? Does that make sense? Because this is normally a tricky thing. And then if you've done lab 3, you've also probably heard us talk about active low versus active high stuff, right? And then this can be confusing with the pull up, pull down. But when we talk about that, you can think of what happens when you click the button, right? What happens when it's active, when you're active on the circuit. In this case, when you push it, it goes low, right? So this is active low. because when you push it, it goes to 0, right? And in this case, it goes high, so this is active high, right? So in lab 1 and lab 2, when you were using the STM board, right, and you were clicking the blue button and turning on the blue LED, that was active high, right? So that means the circuit was using a pull-down resistor, okay? And then if you've done lab 3 and you've worked with the FPGA, you know that the LEDs turn on when you write a 0, or the buttons give you a 0 when they're pressed. So that would mean it has a pull-up resistor. Does this make sense? Do we think we feel comfortable with pull-up, pull-down?
So active low, like automatically, like if it's a button that's active low, that means when it's not pressed, it is gonna get pulled high. Like that's just what it means.
Yes, because if it didn't do that, it just wouldn't work, right? Like there's just no functionality there if it's not pulled to high by default. Yeah. Yeah.
Could you explain how do we see if it's pull up or pull down resistor? For example, if you if in the exam it gives you a circuit diagram and to let you determine if it's a pull down, pull up, how would you do that?
Yeah. So exactly what I said. The only way that works is if there's some sort of switch or button, right? That switches the voltage onto your pin. So it'll probably look something just like either of these. And you just have to look at, again, when it's not being acted upon, right? What is the default value? And whether that's pulling it up to high or low.
So not being acted upon, basically the switch just acts like a high impedance, so no current will pass through.
Exactly. It's not connected, right? What switches literally do is they connect two pieces of metal and allow current to flow, right? So yes, exactly like that. Okay. Yes. Any other questions about pull up, pull down? Oh, cool. Okay. Output buffers. Yes. So they look like this. They take in whatever input. And what they're supposed to do is output the same exact thing over here, but without letting this part of the circuit interfere with the input at all, okay? So to the input, it just looks like an empty node here, right? And then you have your wire here. So it looks empty here. It's just putting whatever voltage, like let's just say it's 3 volts. It's putting whatever voltage here, okay? And with this output buffer, it puts the same exact voltage on the other side of the output buffer. Yeah, okay, let's go through a circuit example where like you can see the difference, I guess. So let's go for our 3 volts. Let's make our resistor divider. Okay. So let's say this is 1K, this is 2K. Okay. So what we would want or expect from this is to get 2 volts on this entire node, right? If we imagine this isn't here. We add this resistor. Let's say we add something that has an equivalent resistance of 2 kilo ohms, okay? So what we would actually expect now is the equivalent resistance of these two is 1 over 2K plus 1 over 2K, right? Which ends up being 2 over 2K. So our equivalent is 1K, right? So if we redraw the circuit with that in mind, it actually looks like 1K and 1K, right? This is what the equivalent resistance circuit would look like. So in the middle here, we would actually get 1.5 volts, which is bad. We wanted 2 volts. So what you can do is you can take this entire circuit, same exact thing, 3 volts, resistor divider, 1K, 2K, and you put an output buffer here. 2K, okay? And so what's gonna happen is to this side of the circuit looks like this, just as we had it before, what we expect, right? So it's gonna put 2 volts here, to this side of the circuit, it's going to look like this isn't here, and that there's 2 volts. So you can think about it as a power source with 2 volts and a 2 k ohm resistor, right? This is all this side of the circuit sees. It essentially isolates the 2 while allowing the voltage on the input to propagate to the output, okay? How this actually works is a bunch of magic. It's a bunch of analog circuit stuff that I don't truly understand. It also has resistors, a bunch of feedback loops, stuff like that. But this is all you need to know about it, right? It isolates the 2 sides of the circuit from each other while propagating whatever voltage here onto the other side, okay? And again, don't worry about this for this exam. This will be an exam 2 thing, because this is very common when you're using DACs. Okay, we talked about ADCs, analog to digital converter. DACs are the other way, right? It's a device where you can give it a digital value, and it'll output an equivalent analog value, right? So by giving a digital value of 0 to your DAC, you can output 0 volts on whatever pin, or if you give it, it'll make sense later, 8,191, it'll output 3.3 volts, right? And you can do anywhere in that range. So it allows you to control it like it's analog, but digitally. How those work is a series of voltage dividers with a bunch of switches between these, okay? This doesn't have to make sense right now, but it's a voltage divider with a bunch of switches. And you're going to use that voltage for something, right? So you're going to put a load onto the output of this DAC, right? Otherwise, you wouldn't have any purpose for it. As we talked about before, when you have the voltage divider and then you add a resistor onto the output of it, it's going to draw this equivalent resistance down. And let's say you were expecting 2 volts here. It would be lower, right? Because you're adding a parallel path, so maybe it gives you 1.6. That's bad. You want to exactly control it, right? So what's super common that they do is right before it goes off to the pin and you're allowed to use it, they'll put an output buffer on it. So that whatever voltage you actually selected using your digital value here, 2 volts, actually propagates to 2 volts on the outside, right? So that's a typical application of it that you're going to learn about later. Does that make sense? Output buffers, yeah. Okay. Cool. Any other questions? Sweet. All right. Well, that's all I have. So yeah, if you guys have questions, you can ask me now, ask me any other time, open lab, anything. Yeah, post on Piazza if you have questions tonight, if you're thinking about it later. And thank you all for coming.
Can you just one more time, like, enumerate what the circuit's concepts that we should be familiar with for exam 1 are?
Sure.
Thank you.
Yeah, have a good one.
So it was like resistors, capacitors.
Yes. So the main thing I said, pull up, pull down, right? Know those circuits and what pull up, pull down means, right? Voltage dividers,
Right. Oh.
right? We might ask you what the current through something is, right? So that would be simplifying the resistors down and then finding the current that way. We probably won't ask you to make a circuit with a capacitor, but you should know what they're used for, right? For smoothing stuff out. You remember in homework 1 where we asked you had the circuit and it was switching the output super fast with the switch, and then we told you to add the capacitor, and you saw how it was switching slower because the capacitor had to charge and discharge, right? You should know like what adding a capacitor to the circuit would do, something like that, right? I'd say that's probably.
Hey, can I ask a question really quick?
Yeah.
So I was wondering with the LEDs and the current limiting resistor, so like, what actually determines, so we said this is
Somewhat
V and this is I and it goes like this. So what will the current through the LED be like entirely determined
That's the clear.
by the resistor you put in series with it? If you, so like let's say this voltage is 3 volts and you put 3 volts and you have an LED and then you have this guy. So
I need to connect this to that.
Yeah. would it,
This is right. This is right.
I don't know if,
Okay, so this is why we had you do.
Does this?
I don't remember.
Okay.
So we had you.
Yeah, well, I didn't do any of the 32s, but I'm talking connections.
Next. There's nothing next.
Oh, okay, yeah. These I don't
So
know.
this is like pretty simple.
Was current limited to 10
Yeah, I was
milliamps.
doing this like last
So what
night.
the diode is going to
so we
do,
have fixed both,
This last.
you set a maximum here,
maximum.
but not necessarily has to be 10 milliamps.
Okay,
Right.
okay.
You said we have to put 10 milliamps.
Okay,
Okay.
I feel like my answers aren't really. I think I answered them mostly like you. I just was like, okay, I'm gonna give like one sentence and call it good. Oh yeah.
This is the voltage at 10 milliamps. This is the voltage we want.
Alternate function.
Oh no, I'll do like once input, once general. I just copied exactly
Wait,
what
because
they
I was like, wait, I don't even know what this means, to be honest.
I like
Okay.
whatever
Did
is
you
in
get,
it.
did you get 8 from 10?
Sure gonna drop 1.6 volts. Like that's just how this curve works, right?
Yeah, I don't know what I did for that.
Was it high?
Gives us.
I don't really remember though.
So we know this is gonna drop 1.6 volts. So this needs to drop 1.7 volts, right? So then we can just do 1.7 volts equals.
Because you're high on life, you're happy, so you're like high, you're not low. Because when you're sad, you're like down at the low.
You get your resistance, right?
Yeah.
Like you have a feeling of euphoria.
So yes, it is entirely determined upon
What's the new version of it?
because this resistor.
There's no way.
How much current?
I found out the other day that, like, not the other day, but I found
They
out that,
kind
like,
of
not always
depend
like spicy, like spicy pictures.
Because let's say you choose.
That is just lot. Yeah, that is just like lot. They just say lot. And I was like, I didn't know that.
I don't like
I
that.
literally was like, I
Well,
didn't think you would use that.
Now the voltage drop is going to be a little different over
Right.
the diode, which is going to cause a little bit different current
Yeah.
because you're dropping a different voltage here. So that's why it's better to find the exact current, or the exact voltage your diode is going to drop at the specific current that you already know you want.
Okay.
Right.
So this is still a deterministic relationship, it should kind of explode, so we like fix a specific point
Exactly.
on it.
Exactly. You let this go up too much, it's just going to blow.
Okay, so we decide a current and then we can decide the resistance.
Exactly.
Hi. Oh, hi.
And the other thing, I kind of didn't fully understand the Zener diode.
Sure.
So basically, you said that this was the Zener diode. I don't remember how you
Wait,
diode.
It's just the diode. Yeah.
that's crazy.
Okay. Okay, yeah. So it goes in the reverse direction.
Uh-huh.
So
Well, Fela.
Wait, no, I heard
it's gonna have a reverse bias.
Yes.
When you hang around.
That's what we want.
Yes. Because that means current won't go through there under normal conditions. Right.
Okay, so under normal, so it still kind of has like the same kind of curve.
Yes, for sure.
Okay. So under normal, there will be nothing going through this, and then if it goes higher than like the breakdown, then you're saying current will go through.
Fela.
Let's look at
So
it.
that won't change the voltage here, right? Or it will.
All
It
the
will.
things are.
Also,
Also, I don't want to
leave
do
our stuff there, so we'll probably tweak the one next to us.
So it will kind of like eat up all the voltage drop pretty much, right? And this will just be like 0, like what
Not
is
quite.
this?
I didn't
Not
set
quite zero.
I
It'll
didn't
eat
set
up all the extra voltage.
Okay.
Right. So let's say this is supposed to be 5.
What if we just change out that
Let's say the
thing?
breakdown is 5.5. And let's say you were going to have a peak that jumps up to 6. Okay.
monitor.
You don't want it to get to 6, right? So what's going to happen is after it gets above 5.5 here, this is going to break down and allow current to go through. If it gets below 5.5 again, it's going to block current from going through.
Right.
So it's going to dissipate all extra current.
Okay, you know what? Fallon, protect your computer.
So even when this goes up to 6,
I need these ports. Like I charge through these ports.
You do 470.
This is still 5.5 or no?
Yes, exactly.
I want food.
Exactly.
Do you want to eat out or do you want
Because it's the only load on the.
Well,
It like manages it with
in
the
theory,
external thing.
yes. This is extra to add power protection to your system.
Okay, it's just able to figure it out.
Well, so it has a separate number, right? So this is the other side of the diode curve that you have, right? And so
you?
at this point, when it jumps up a bunch, it's going to
So 5.5 is breakdown or 6 is breakdown?
5.5 is
Okay.
in our imaginary scale,
Yeah.
right? So, sorry, when I say it would get
Literally like
let's
same
say-
distance.
let's say-
One is like 5 steps away.
Right.
Right. So
Oh, it's kimchi.
the voltage curve,
Yeah, well he could do Chinese.
6 volts, 5 volts,
Yeah.
right? What would happen if you have the Zener diode at 5.5
Mhm.
is it would
Okay, a burger is with like something
No,
else, not chicken.
no. If I see buns, it's a burger.
It says chicken sandwich.
because
Chick-fil-A
That's
don't got
Korean.
burgers. Chick-fil-A got chicken sandwiches too.
No, it's a burger.
You don't see a chicken burger, you see
They're Korean.
Okay,
so
look
we'll
at the
forgive
rest
them.
look at the rest of the
You're giving it positive over here and negative over here.
Uh-huh.
So it's getting a like current in this direction.